Hey guys, this is Siri and I'm back with another PyTorch video, and today we're going to be talking about Autograd. It's a very handy tool that PyTorch gives us, and we're going to be talking about why we need it, what it is, and how it all works. Okay, and so when we train a model, right, we are we're making it learn some data, learn some patterns, and we're in the hopes of making some accurate predictions. But the thing is, at the beginning of your training, you're not going to have like perfect results, right? That's what training is all about. That's what machine learning is all about. The machine and the model learns from its past mistakes and what it got wrong. And so a good measure of that is our loss function, which just tells us how far our predictions are from the actual output. But the question is, how does our model really learn from that, and how does it correct itself, and how does it make its predictions just a little bit closer to the actual value? And the percentage of, how do we make the percentage of correct predictions go up, and how do we make that accuracy grow up? Well, it all lies in the computations, right? That's what the whole process is all about. It's about the computations. And so the main part and the main component we need to look at are, or the components we need to look at are our parameters, which are our weights and our biases. And so whenever we get something wrong, we need to make some adjustments, and we make these adjustments to the weights and biases. And well, how do we do that? How do we change our weights and biases so that our predictions are better, so that they're more accurate? Well, the answers lie in something called a gradient, which is just the derivative of our computations of the new values we get. And this whole like finding derivatives thing, this algorithm you would call backpropagation. And this is where the weights, like I said, are adjusted to the gradient of our loss function. And right, because that's where we need to make adjustments. We need to look at the loss. We need to look at where things are going wrong, and we need to make adjustments there. So we take the gradients of our loss function with respect to the parameters that we're talking about. And you see the like take the gradient with respect to, you see this like derivative notation and this language here, like dy dx, take the derivative with respect to x or something. But it's kind of hard, right, to take the derivative of each parameter. I mean, you have access to the parameters, but you wouldn't want to like take the derivatives of each and every one of them, because there's so many. Especially if it's like a complex model, you're going to have many different parameters, and it's going to be difficult to take the derivatives and compute the gradients for all of them. But thankfully, PyTorch offers us PyTorch.Autograd, which allows us to compute these gradients, get this, in just one line of code. And that line is dot backward, okay? And Autograd is basically this built-in differentiation engine. Okay, you see the differentiation taking the derivatives. And if you're not familiar with that, don't worry. It's just like taking the instantaneous slope of like in the context of R, like mathematical function, right? Because it all lies in the math here. So, okay, but Autograd is a built-in differentiation engine. Okay, wait. Autograd. Okay, great. So let's just take a simple example. Let's just take a regular linear layer, okay? And it has our basic input, right? Let's just call our input x, okay? Let's call our output y, and let's call our parameters w and b, which stand for weights and biases. And we have some loss function, okay? And we can do this this way. So we can do import torch, right? We can set it equal to a random tensor. And when I mean random, it's just like a random tensor that I came up with. It's not like an actual random tensor. So it's not like torch.rand. I'm gonna make it full of ones. Okay. Torch.ones and 5. Okay, so that's gonna be our input tensor. We have y equals torch.zeros. Okay, 3. This is what we are gonna set our output equal to. Our w, so torch.rand n 5, 3, and these are just the dimensions, what I'm putting here, in the parameters. 5, 3, and we have an interesting thing here. We are gonna say requires grad, and it's a Boolean value. We're gonna be setting it equal to true. Okay, and we'll go over that in just a second. We'll go over what requires Autograd actually does. Okay, so b is equal to torch.randn. Okay, 3, comma, requires grad is equal to true. Okay, so that's that, and z is going to be like the actual computation. We're going to do a matrix multiplication. So torch dot matmul, that just stands for matrix multiplication. And we're going to be multiplying x and w, and we're going to add our b. You see the y equals mx plus b format or like structure here. So y equals mx plus b, where m is actually our w and our b is just our b. Okay. And so loss is equal to torch.nn, that's where all the loss functions are, and they're in something called torch.nn.functional. They have tons of functions. I would definitely recommend checking that documentation out. So, okay, and then this is going to be our loss function, binary cross entropy. Okay, with logits. Okay, and z, comma y. Okay. Okay, so great. So you see that like what I talked about before, like the parameters are the things that we optimize and that the things we need to adjust. And so since these are the things that we need to optimize, if you're familiar with calculus, you'll remember these like optimization problems. And yeah, that knowledge will really be helpful here. But it's okay if you aren't familiar with it. Okay, but since w and b are parameters, we're going to be taking the derivative with respect to those variables. Okay, and if we want to do that, right, that's why we set requires grad is equal to true. If we want to take that step of really like taking the derivatives, going back to optimize our model, and to change up our parameters so that they result in more accurate predictions, then we're going to have to be setting requires grad equal to true. So you can do it here when you're creating the tensor, like we're doing like here with W and B, or you could do it later by saying x dot requires grad and then pass in true. If you don't want that to be the case, then you would pass in false. Okay. Okay, and if you recall, we've talked about the forward method in another video, and that's a step where we do all the calculations, but the dot backward method, as you would imagine, it goes backward, it retraces the steps of our computations that we did in the forward method, and it goes back and it computes the derivatives. Okay, and that would be in the back propagation step. So that's just the term for it. Okay, and let's compute the gradients. Okay, let's run that first. And let's say loss dot backward. Remember, because we're taking the gradients of the loss function, because that's where we see what's going wrong and what's going well. So we just call dot backward. It's great. Okay, and let's just print w.grad. Let's print b.grad. So here you're going to see the values of the derivatives that we've just computed in our loss.backward. So you see here, 1, 2, 3, 4, 5 by 3, 5 by 3, and you see that here in our weights, torch.rand_n 5, 3, and you see a 1 by 3 tensor in like for our B. Okay, great. And you can also disable gradient tracking if you don't want to do that. And there's several reasons why you may not want to track the gradients or derivatives. And one of these include, like, if you just want to do the computations and if you just want to go forward, and you don't really need to go back because it's a waste of time, it's a waste of like everything. If you just want to go forward and you don't need to go back, then you can do something called dot detach, or you can also use a with block. Okay, so an example of this is if you say with. Okay, let's do an example where requires grad is true, and let's see what it's like when it's not true. Okay, so let's use a variable z. Z is equal to torch dot matrix multiplication, or matmul. Okay, x comma w, same thing. We're doing the same thing here. Okay, so and then print z dot requires grad. Remember, this is a Boolean value. And let's do a with block. With torch dot no grad. This is an attribute. Z is equal to torch dot matmul. X comma w, same thing, plus b. Okay, and let's print the same thing. Z dot requires grad. Okay, and let's see where it's enabled and where it's not enabled. So yeah, you see true and you see false. So you see we set requires grad is equal to true, which is why we get a true value here. So actually, wait. Actually, it's on there by default. So when we say with torch.nograd and we set it equal to the same thing, we're saying torch.nograd. And then we get these Boolean values. Okay? And like I said before, you can also use the detach method. So let me just copy paste it because we're using it a lot. And let's say z detached is equal to z.detach. Okay, print z detached dot requires gradient. It requires grad. Again, it's false. Okay, because we're using the dot detach. Okay. And an interesting thing to note, if you want, is that when we're going back and we're taking the derivatives, we're actually using the chain rule in calculus. And the reason is because, like, if we have an input, we have many layers, right? So if we have an input, they're not layers, it doesn't have to be a neural network, but like there's many inputs and many outputs. And so we have an input and then we have an output, and this output is going to be the input to another computation, which is basically the same thing, the same conditions for chain rule, whereas like the output is the input of another function. And so yeah, that's just a side note. If you wanted to learn more, you could definitely read the documentation. Okay. Yeah, I think that's it for this video. I hope you learned like why we use Autograd and how it makes our lives so much easier. Like if you wanted to compute the derivatives by hand and if you wanted to do it manually, then go ahead. But I would definitely use like the .autograd to just do that computing in one line of code. Seriously, that's insane. And the way it does it actually is by tracking the history of computations, and it has a log, and so it can go back and compute. Okay, and it's all about like the parameters and the weights and biases and just adjusting them to make our model perform better. Okay, yeah, thank you so much. I hope you learned something new today, and don't forget to like, comment, and subscribe. Thank you so much. Bye-bye.